Good morning, everyone. We'll record this video in English, so it might be useful to more people. In this work, I will try to replicate some of the results of this Japanese team. They have more than 5 papers, and the paper that I'm particularly interested is the how they maximize torque volume density, and they did in a way that they set an initial model parameter with a motor model with those parameters, and they swapped the variables, the main variables, the main constructive parameters, to see what had the best torque volume density. I will show here how I did this. Those are all the formulas that I used, and those are the main parameters. For example, if I try to change the height of the winding, all the rest of the motor should change accordingly. For example, if I set to 1 millimeter, the winding becomes thinner and the stator pole becomes wider. Um, Let me change back to this, which is more real. And if I do this, the number of conductors should be changed accordingly. Right here, I have 38 conductors, and if I change the winding height to 4 millimeters, I should have less conductors. And the excitation of these motors, these models are also in function of the constructive parameters and the current density. They try to explore the current density, and there is also a swapped parameters in their simulations. So the motor model should maintain the air gap, and its bands should all be parameterized by these main parameters. If I change here, for example, the stator height, stator pole height to 12 millimeters, all the motor should be shifted, should be thinner, and the air gap and its band should move accordingly. So this is the core of this work, the simulations, and I can add a sweep over parameter. For example, the stator pole height itself. I define a step and I add here, so I have all of it. Furthermore, the simulation time I set to a amount of time that I know it is the same amount of time that I should need to energize the coil if I apply a voltage drop. And for the moving simulation, I also defined all the parameters accordingly. The degrees per second is based on the simulation time and the, the dwell that I want, and all the other things. The excitation and the winding is done in this manner that they described here, where they say that the area is calculated with this formula, which is the height of the starter pole and the height of the winding that I just showed. And the winding has a non slot fill, which is set. This is the conductor um, profile. It's squared in this simulation. It could be round, but I can also tamper with the fill factor because it will all be reflected in the number of turns that is capable of occupying this cross section here. So the excitation is the current, which is defined by the current density times this space, and the excitation needs to be the current purple. Otherwise, if I perform a simple calculation here in the calculator, I can show you current density, and I have a geometry terminal 04, which is one of those terminals that are being excited, and I calculate the integral of the normal. I will have the current that is passing through that surface in a normal direction. And I can also prove what I've just said by dividing by the number of conductors. Now I have the number of amperes per per strand per conductor. So I performed some of those experiments they proposed and a few more, and the results are published in this paper here, and the results are quite positive. All of the results are basically the same. The work is of their all their work is pretty much complete with data, so it's easily replicable if you try hard enough. There are some tricks. For example, you need to define similarity of triangles so you can play with the winding and the starter poles. As you can see here, I have some geometry, basic geometry, nothing that fancy, and I will expose some of the results. This is pretty basic. If you saw my other video, is just the moving torque and the moving position. They are all already preset here. The torque density otherwise is a formula. This one I plot the max torque so I can see the maximum of the torque in for the different current densities. So you need to, to draw a simple formula. Winding also is direct, and the output variables you can see the integral is just the integral of the moving torque divided by the volume, and that's it. The inductance is the flux divided by the current at the moment, and that's all. So this is it. There's nothing else to say at the moment. Is extensive set of simulation, but once you made your setup, is just waiting for the simulation to be completed and analyze the data. If you didn't screw anything like the excitations or the number of strands, if you do this table correctly, all the rest of the work should be relatively easy. So this is it. The only thing that is worth mentioning is that for a moving excitation, you need to have, and you don't need, it's easier to have circular instead of polyhedron, so it won't clip one on top of the other, one inside of another. And for simulating this, you can say right here, assign mesh operation, and you can make surface approximation, manual settings, and you can set this to 3 degrees, so the solver won't will not try to will converge easier. This is it. All the rest is pretty standard, more or less. Goodbye. I hope you all enjoyed.